Hi everyone, and welcome to another seminar of Physics Latam. Today we are very honored to have Professor Hong Liu giving a talk on entanglement, von Neumann algebras, and the emergence of space-time. Hong Liu is a professor at MIT. He has been interested in issues related to quantum gravity, such as the quantum nature of black holes and the Big Bang singularity, using the framework of string theory. He also studies quantum matter systems as holographical duals to quantum gravity models. More recently, he's one of the pioneers in studying von Neumann algebras to understand the emergence of space-time, which is the main topic of this talk today. Please remember to raise your hand at any point if you have any question. And now I leave you with Professor Hong Liu. Please go ahead.
Okay, yeah. Thanks a lot, Daniel, for the introduction and for the invitation to give the talk. It's a pleasure. So if you have any questions, don't hesitate to ask. Just interrupt at any time. So here is a very rough plan, what I'm going to do today. So first, I will give you some motivations for what we are going to do. And then I will discuss a little bit entanglement, von Neumann algebra, and the relation between them. And then I will discuss how we can understand the emergence of space-time from von Neumann algebras. So so of course Einstein told us, like in special relativity, space-time should come together. Space and time are not separate. And then in general relativity, he told us that gravity is actually equal to space-time. Okay. And that means that since gravity is dynamical, that means the space-time is a dynamical object. Sorry. Yeah, that space-time is a dynamical object, and it can evolve on its own, but can also curved by matter in it. Okay, so so the dynamical variables for gravity is just given by the space-time metric, and then can describe distances, the flow of time, curvature, etc. And then the dynamical equations are given by these Einstein equations, which tells you how the Einstein tensor is related to the matters, the stress tensor of the matter. Okay, and so Gn here is the Newton constant, which essentially gives us the strength of gravity, and which also characterize the matter's ability in curving the space-time. Okay, so if you have a larger, for the same T mu, if you have a larger G Newton, then of course you have a bigger effect on the right-hand side. And so the other pillars of, the other pillar of 20th century physics is quantum mechanics. Quantum mechanics, of course, governs many aspects of our life. All the electronics are enabled by quantum mechanics. And it's widely believed that space-time and gravity must also be quantum. Okay, but even though there has not been any direct evidence, we don't have any experimental evidence that space-time and gravity is quantum. Okay, and we believe so just because of the internal consistency of the series. And in nature, gravity is very weak. Okay, under this you can see immediately, say if I raise a pen from the table, and by doing that, using just slightly tweak of my muscle, I can already overcome the gravity of the whole Earth, say on the pencil, on the pen. Okay, and so the gravity is very, very weak. And the fact that gravity is weak can also be seen from that the G Newton is a very, very small quantity. Okay, using our standard scale, you can see that the G Newton is very small by working out, say, the length scale, which you can construct using the G Newton. Okay, so say, so this is the fundamental length scale which you can construct with G Newton, which is the so-called Planck length. And Planck length is extremely small number measured in our ordinary time scale, length scale, which we are familiar with. Okay. And so that means, okay, so that means the detection of the quantum gravitational effect. Yeah, actually, I think, 1 second. I think I may have, 1 second, I think I may have, there's something wrong with this slide. I think I may have, I forgot to delete this slide. I think I have a, 1 second. Sorry, things are very slow, seems to be. Wait 1 second. Yeah. Want to go away from the, oh yeah. 1 second. Yeah, sorry. Yes. Yeah, that slide I should have supposed to delete it. Okay. Yeah, that's okay. We can just continue. And G Newton is a very small quantity. And so this can be seen by the Planck length, say it's a very small parameter from our usual scale. And so for physical process, say for example, for physical process of characteristic length L and energy, which is just governed by the uncertainty relation, say in quantum mechanics, say h bar divided by L. And then the fine structure of gravity is just characterized by the Gn, G Newton, say alpha G, which we define as a dimensionless constant. It's essentially the proportional to G Newton times E squared, the energy. And which you, in turn, you can write it in terms of the ratio of the Planck scale, Planck length square divided by L square. Yeah, so your typical length of your physical process. And so, yeah, of course, for the typical process of the L, which we are familiar with, this number is extremely small. Okay, so that tells you that the gravity is extremely weak. And the fact that the alpha G is extremely small for most of the scales we are interested. And so that tells us the detection of quantum gravitational effect is extremely difficult. So if we want to measure direct quantum gravitational effect, we have to go to such short distances. But on the other hand, we now believe that small distances of G Newton is actually needed to have a large universe. So small distances of G Newton, as we said here, means that the quantum fluctuations are only quantum gravitational fluctuations are only at a very small scale. Okay, so they don't affect, say, the physics of our ordinary life. They don't affect the galaxy formation, etc. Okay, and so we believe that it's actually important in order to have a large universe, that in order to have things like a galaxy, to have stars, etc. In human beings, you actually need quantum gravitational fluctuations to be small. And so that presents the dilemma, okay? So in order to measure the quantum gravitational effect, so we have to be there, okay? And in order for us to be there, but then the G Newton have to be very small. And that means it's very hard to measure the quantum gravitational effect. So the literature is very good at actually hiding her secret, okay? So even though the quantum gravitational effect is very small, theoretically it's very small, and we don't have any direct experimental evidence to for the quantum nature of space-time. Of course, that has not prevented physicists from thinking about the problem. Okay, actually, physicists started thinking about this problem very early on, not long after, say, the discovery of quantum mechanics and the general relativity. Okay, already in the early 1930s, and Bronstein had already started thinking about quantizing space-time. Okay, and so very natural idea, say, of quantizing the space-time is the following. So general relativity is a classical field theory. Okay, so this is a classical field theory of a metric field. And so to go to quantum, we can just quantize this classical field theory and treat it as a quantum field theory, just as in the case of electromagnetism. Okay, so classical electromagnetism is a classical field theory, and to describe quantum electrodynamics, we just quantize the classical electrodynamics, and then we get the QED, and which has been phenomenally successful. Okay, and so we can just try to repeat the same game for the Einstein theory. Okay, just treat it as a quantum field theory, and treat it as a field theory and just quantize it. But then when you do that, say over the so people already started doing that in 1930s, and so now it's almost, say, almost 100 years later, and this approach still has not been successful. Okay, so there are many difficulties, and including both technical difficulties and conceptual difficulties. And the conceptual difficulties involving the following. So let's consider, say, a very simple process. Say, if you have, say, two heavy particles, and then which their watt lines are represented by these two lines. And then they can exchange gravity, then they can have gravitational interactions between them. So when you quantize general relativity, then the quantum corresponding to the metric is the graviton. Okay, so then you will have graviton exchange between these two, say, heavy objects. And so when you try to calculate this kind of process, and then you immediately find UV divergences. And in fact, all such processes, okay, any such generic processes, they're all UV divergent. And the standard quantum field theory treatment of renormalization actually break down for such theory. Okay, and using our standard QFT language, and what this implies is that a general relativity as a quantum field theory is UV complete. And it means that in order to make sense of this theory, say, at short distances, and we actually needs to complete this theory by something else. Okay, so by itself, it's actually not a self-consistent theory at short distances. And so this is one indication that the this approach actually has significant conceptual difficulties. So so after this almost 100 years of attempt, so many people have now start suspecting maybe quantizing general relativity just a wrong idea. Okay, and in particular, so maybe space-time is not a fundamental object, but emergent. And if that's the case, then quantizing general relativity will just not, may help you to understand, may help you to understand the low energy behavior of the quantum gravity, but will not be able to reveal its fundamental nature. For example, so the analog, say, for example, is a fluid. So imagine the situation, we actually discovered the quantum mechanics first, okay, before we discovered the fluid mechanics. And then when we discuss the fluid mechanics, and then before we understand the fluid, okay, suppose we understand the quantum mechanics first before we understand the fluid, and understand the fluid that is made of the molecules. And then suppose we try to understand the fundamental nature of the fluid, and then of course the natural thing to do is that you just use the quantize the hydrodynamics. Okay, and then you can try to quantize the hydrodynamics. But even though that may give you some quantum behavior of the fluid, but as we know, there's no way that can reveal the fundamental nature of a fluid, say as say a continuum approximation, say of the large number of molecules. Okay, and that just will the approach it just won't work. Okay. And so yeah, if space-time is indeed not fundamental, but emergent, and then what are the fundamental degrees of freedom, okay, of gravity? And so the question is that is space-time emergent? And so there's actually a strong hint that space-time and the gravity is indeed emergent. And that comes from string theory. So string theory says that actually the fundamental particles we observe in nature, they're actually not really fundamental. They're actually not point particles. They're excitations of some fundamental strings. Okay, so the fundamental object, say in nature, are actually one-dimensional object, not point particles. So we have a one-dimensional object that naturally introduce a scale, length scale. So what is normally called the string length, which characterize the scale, the length scale, say, of the fundamental strings. Okay, then the string theory says at length scale much larger than the string length, then you cannot resolve the size of a string. Okay, then the string just behaves as point particles. Then our usual field theory then applies, and in particular, say our usual a continuum picture of space-time applies, and then you just see a continuum space-time. Okay. But now if you have high enough resolution, and then is there a question?
Yeah, I would like to ask, like, these UV divergences that we obtain at quantizing the metric field, are they non-renormalizable?
Yes, they're non-normalizable.
Okay.
So they're perturbatively non-normalizable. And so we don't know how to, and there have been dreams. Okay, people have speculations. Maybe non-perturbatively, if you're able to treat the G Newton constant non-perturbatively, and maybe they become renormalizable. So there has been a huge amount of attempts, huge number of attempts trying to show that, but none of them has been very successful. So that possibility has not been ruled out. But the the lack of success also have motivated people to look for some other possibilities. Mm-hmm.
Thank you.
Good. So so from string theory point of view, now if you have enough resolution that you can really resolve the string as one-dimensional object, and then space-time will look very different. Okay, then your continuum space-time then actually will look like, say, a large collections of fundamental strings. Okay, it's like, say, a continuum fluid can be viewed as a continuum fluid is more like a continuum approximation, say, of a large collection of molecules. Okay, and so this gives you the hint that space-time, string theory tells you that space-time is not fundamental, but rather an emergent concept at large distances, which you cannot resolve the strings. But in string theory, so string theory introduced a length scale, which is the string length. Then it's a natural question to ask, how does the string scale, string length, compare to the Planck length, which we mentioned earlier, is the fundamental scale characterize quantum gravity. But in most string theory, we actually know how to treat, okay? Means that the string theory at weak coupling, which this string picture actually applies, the Planck scale is actually much larger, much smaller than the string scale. So that's says a lot of possibility that actually maybe in the genuine quantum gravitational regime, maybe at the scale of the Planck scale, even the string picture may not apply. Okay, indeed, there are indications that the stringy description may not be fundamental. Okay, and the most important indication that even string picture is not fundamental comes from something called the holography and the so-called ADS-CFT duality. So let us consider, say, anti-de Sitter spacetime. So anti-de Sitter spacetime are class, say, are spacetime, homogeneous spacetime of lactive cosmological constant. Then, of course, the de Sitter spacetime itself is a homogeneous spacetime, but you can consider excite matter or gravity inside the spacetime. Okay, then you can, in principle, say, for example, in the G Newton goes to zero limit, in the limit which that the scale of the anti-de Sitter spacetime is much larger, much larger than your Planck length. Okay, and then you have what we call large universe. And in this case, in principle, just like in our universe, you can have galaxies, you can have stars, in principle, have humans, okay, in anti-de Sitter spacetime. Of course, our current observation that we are living in the de Sitter spacetime is a positive cosmological constant. But in principle, the same kind of physics can happen in the anti-de Sitter spacetime. Okay, so anti-de Sitter spacetime can be visualized as a solid cylinder. Okay, so it has the form. Yeah, you can imagine it as the interior of a cylinder. Okay, and with time going up, and at each constant time slice, you have a hyperbolic space. Okay, and then you can conformally transform this space-time so that the boundary at, say, the space-time infinity lies at the finite distance away using the so-called the conformal mapping. And then the topology of the space-time, it just as indicated, is like a cylinder and with a cylindrical boundary. Okay, so remember this boundary actually, even adjoined at the finite distance away, actually they're at infinite proper distance away, but they have the topology of a cylinder. And so at each constant time slice, the boundary is like a sphere. Okay, and it's a very large sphere. Okay. You can also, a very large sphere, you can also sometimes approximate it by a plane, and sometimes we often use that approximation. Okay, so so now you can consider quantum gravity in this kind of anti-de Sitter spacetime. And in this case, actually, we have a remarkable relation from Madisina proposed in 1997. Is that the quantum gravity in this kind of anti-de Sitter spacetime turns out to be equivalent to some boundary theory living on its, some quantum field theory living on its boundary. Okay, so we call it the boundary theory. And so this boundary theory is often, say a conformal field theory, say we call it the CFT, or some quantum field theory. Okay. And so a feature of such kind of boundary theory is that they are described by their fundamental degrees of freedom are matrices. Okay, so essentially they are essentially a field theory of matrices. And those matrices are characterized by a rank n. Okay, just a matrix of a rank, and just n is the rank. And so the G Newton, on the gravity side, the strength of the gravitational coupling, and turns out to be related to 1 over n. So that means in the case which G Newton is very small, means you have very large universe, and then this n is very large. Okay, so that intuitively makes sense. When n is very large, means you have lots of degrees of freedom. Okay, and you have lots of degrees of freedom, that means that you can actually describe, lots of, when you have more degrees of freedom, of course, you can describe richer physics, say like galaxies, stars, or human beings, etc. And then the semi-classical gravity limit, okay, then corresponding to n go to infinity limit. Okay, so of course our in our universe, G Newton is very small. So what we describe, the physics we describe is all the physics in the G Newton goes to 0 limit is what we normally call the semi-classical physics, and that is the regime which we have a well-defined concept, say, of space, time, and etc. Okay, and when G Newton is finite, then space-time fluctuation is very big, and then we can no longer talk sensibly about the space-time in the way, geometrically in the way we are familiar with. Okay, it's because, say, for example, you can fluctuate from a black hole to a state without a black hole. Okay, and then our ordinary sense of the geometry then no longer applies. So, do you have any questions? Okay, good. So our goal, okay, so now with this framework, now we have a precise way to formulate the question of the emergence of space-time in the G Newton goes to 0 limit. Okay, in the semi-classical limit, which we expect which the space-time to emerge. Okay, so now we can formulate the question precisely as how does this box space-time and the associated geometric concept, and such as the metric or causal structure, which plays a crucial role, of course, in the characterize of in generativity, and emerge from this matrix degrees freedom in the n go to infinity limit. Okay, and we only expect this question to make sense in the n going to infinity limit is because at finite n, then the G Newton is finite, then the space-time fluctuates, and then we expect those geometric concepts to break down. Okay, good. So is this question clear? Good. And so there have already been some hints for where does this space-time come from, okay, from this boundary matrix degrees freedom. And so one very crude hint, so one very basic question you can already ask, okay, is that this spark quantum gravitational theory has one higher dimension than the boundary, because there's a radial direction, okay, which is in the present in the bulk, which is not in the boundary. Okay, and so one immediate question you can ask, even forget about the details of the continuum or geometric concept, it's just even where this extra dimension come from. Okay, so now we actually have a well understood. So now we have understood pretty well where this extra dimension comes from. So let me now just consider a single time slice of this ADS space-time. Okay, so the single time slice is just which I draw as a disk. Okay, so the boundary is more like a circle. I represent the boundary as a circle, and the interior is the disk. Okay, it's a hyperbolic, hyperbolic space. So consider this a single slice of a hyperbolic space, okay, with the boundary given by the circle. And now imagine I have two radial locations, okay, 1 and 2, at two radial locations. Suppose I have some cause there, okay, in this anti-de Sitter universe. So the two identical for chaos. So how do we describe this chaos from the boundary theory? Okay, it turns out these two identical chaos at different locations, they actually maps to object of different sides on the boundary. Okay, so in other words, the radial direction in the Bach is reflected in the scale, okay, of the boundary theory. Okay, so the larger scale reflects to something more in the interior of the space-time, and the small scale reflects degrees freedom closer to the boundary. Okay, and of course this is a rather crude understanding of the Bach. Just tells you where this extra dimension comes from. So a more refined understanding of the Bach geometry come from understanding how the entanglement of the boundary theory is represented in the Bach. Okay, so this is the famous Ryu-Takealagi proposal in the context of this holographic duality. So suppose if we ask say consider a sub-region in your boundary, okay, which I call R. Let's ask how this sub-region R is entangled with the rest of the degrees freedom in your boundary theory. And such entanglement is characterized by things such as entanglement entropy. Okay, it turns out from this Ryu-Takealagi proposal, the entanglement entropy for this region R can be characterized by the area of some surface on the gravity side. Okay, so here the details here does not matter. So the claim is that the entropy, the entanglement entropy of this region R is characterized by the area of some surface, okay, on the gravity side. And then this connects. So the area of some surface, of course, it directly reflects the geometry on the gravity side. Okay, so this provides a direct connection, okay, between the entanglement in the boundary system and the space-time geometry on the gravity side. And since the proposal of the Ryu-Takealagi, we have accumulated lots of such kind of examples which connect, say, entanglement on the boundary theory with the space-time on the gravity side. Okay, so we have lots of experience of such kind of relation. But still, we don't have a very systematic picture, like how space-time geometry actually is encoded in the entanglement. So essentially, we have lots of examples, but we actually don't have a coherent structure to understand them. And in other words, is that how actually space-time, we don't space-time emerges, okay, from entanglement. Okay, so that's the question we like to answer. Okay, so in this talk, I will tell you the progress in understanding this question. Okay, so first, I will tell you that the von Neumann algebras actually provide a universal language in characterize the entanglement structure of a quantum system. Okay, and in particular, classifications from von Neumann algebra provide the classifications, say, of entanglement structures of the quantum systems. And so this then I will use the explain how the von Neumann algebra then could provide the powerful language for understanding the emergence of space-time and other geometric notions. Okay, so before going on, do you have any questions?
Yeah, for me, it's not clear yet, like what type of system does the boundary represent? Yeah, like I think I'm a little confused about that.
Oh, good. That's a very good question. So so here, actually, there are many examples of such kind of duality, but in all in different dimensions of ADS space-time, etc. And they are all due to very different boundary systems. And so there are many such examples, and the boundary systems and they can be many different things. For example, they can be anchored to a super Yang-Mills series in 4 dimensions. There can be some 2-dimensional CFTs. There can be other kind of 3-dimensional conformal field series. So by now we know infinite number of examples. So they are all some kind of quantum field series or some kind of yeah. And but the overall theme among all these series they are all described by some kind of matrix equals freedom with the characterized by this number n. So the details of those series are actually not that important. So that's why I didn't describe any specific examples or give you details of such kind of boundary system. And for our purpose, we only need to know that the boundary is some kind of quantum mechanical system whose degree of freedom is characterized by this n. Yeah, by this number n.
Thank you.
Other questions? Okay, good. And then we'll. So now let me talk a little bit about entanglement and von Neumann algebra. So just a very quick, yeah. So you may have studied entanglement in your quantum mechanics class and in textbooks. And so very quick, just history of entanglement. So yeah, so entanglement starts in 1935. So it's almost 10 years after the discovery of quantum mechanics. But Einstein was still plotting to subvert quantum mechanics. Okay, so he was not happy. He wanted to subvert quantum mechanics. So together with the Podolsky and Rosen, they came up with EPR experiments, which in modern language is that they consider, for example, if you compare a pair creates 2 electrons, and then because we pair creates them, and then these 2 electrons, then the state of the 2 electrons is in the particular form, such that the measurement on one electron is correlated with the measurement on the other electron. Okay, and in particular, if you make measurement on one electron, that will influence the measurement on the other electron. Okay, so even they are separated, say 90 years away. Okay, so this is what the Einstein called the spooky action at a distance. And so EPR wanted to use such kind of thought experiment to argue that actually quantum mechanics is not complete by itself. Okay. And in the exactly the same year, so EPR say even though was trying to say overthrow quantum mechanics, but Schrödinger immediately realized, okay, this is actually a crucial feature of quantum mechanics. And then he actually coined the term entanglement. Okay, it's just within the same year. He coined the term entanglement, and then of course, and then put his famous cat in such an entangled state. Okay, between the life and the death. Okay, and of course, around the same time, this EPR paradox was refuted by Bohr. So Bohr very quickly wrote a very forceful refutation of the EPR's argument that the quantum mechanics is incomplete. And the Bohr's refutation was so, say, convincing to the community. And unfortunately, not only did the community accept, okay, the Bohr's explanation, but they also very soon forgot about entanglement. Okay, despite that Schrodinger pointed out the entanglement is actually an important feature, and the community actually soon forgot about entanglement. And only until about 30 years later did Bell actually realize actually entanglement can be used to test quantum mechanics, in particular to perform experiments to show that to distinguish quantum mechanics from classical mechanics, okay, so-called the hidden variable theories, etc. And then again, for many years, even after Bell, and the entanglement was more like some kind of curiosity people used to distinguish quantum mechanics and the classical mechanics. But not until another 30 years later, and when people start thinking about using quantum mechanics to do computation, okay, using say, and for computation and communication, and the people realize actually entanglement can be used as a very important source, okay, for quantum computation and communication. And then people start realize the powerful, okay, implications, say, of entanglement. And then also motivated from that in 21st century, and the people start to realize that actually entanglement plays a key role, not only say for quantum computation and quantum communication, but also in understanding, say, condensed matter systems, in understanding quantum field theory, and in understanding quantum gravity. Okay, it turns out they provide a key role, okay, to characterize those quantum many-body systems. Okay, yeah. And so so heuristically, entanglement characterize quantum correlations among different subset degrees freedoms in the quantum system. Okay, so here emphasize a subset of degrees of freedom. Okay, so this is a intrinsic quantum notion. Okay, and so this is what we normally call the subsystem. And so a famous example of entanglement, of course, is this state, which consists of two spins. Okay, so here you have two subsystems, two spins. Okay, and so this is the entangled state of the two spins, and so for the first spin up, and it's entangled with the down. Yeah, just they have one system one and system two. They have opposite spins. Okay, they're in the superposition of the state of opposite spin direction. And more generally, we can imagine, we characterize entanglement as follows. Say, let's imagine we separate your quantum system into two parts. Say, one part we call 1, and the other part we call 2. And the typical entangled states are the states which you can write as superpositions, okay, of the states in 1, tensored with the states in 2, okay, and the superpositions which cannot be factorized. Okay, so that's what we call the entangled states. So they're superpositions of the states 1 and 2, which cannot be factorized. Okay. And here it's crucial that in writing down entangled states, okay, requires factorization of the Hilbert space. That in order to write down such a state, the full Hilbert space should be factorized in terms of the tensor product, okay, between the Hilbert space of the system 1 and the Hilbert space of the system 2. Okay, that's how we write down such a entangled state. So intuitively, that actually create a little bit tension. So the concept of a subsystem is physically very intuitive. Okay, if you consider some subset of degrees freedom, and then we can naturally think of them as a subsystem. Okay, but mathematically, so in textbook definition of mathematically, to define it is actually highly intuitive. So it requires this factorization of the Hilbert space. We say a subsystem, we can only we define subsystem by factorizing your Hilbert space into the this kind of tensor product. But in general, such kind of factorization structure is actually rather non-trivial requirement on the structure of the Hilbert space. Okay. So this highly unintuitive requirement seems to be a little bit at attention, say, with this physical way, intuitive way we think about subsystem. Okay. Yeah, essentially, yeah. And in fact, there's a lot of tension. In fact, there are many actually physically interesting situations where such a definition of the factorization actually breaks down. Okay, and there we can actually sensibly talk about subsystem from our physically, but somehow there does not exist, say, factorization of the Hilbert space. And so this happens in particular when there's actually an infinite amount of entanglement. Okay. So the basic picture is the following. So when you have an infinite number of degrees of freedom, for example, if you have a statistical system, say in the thermodynamic limit, or you have, say, quantum field theory, and then you have an infinite number of degrees of freedom. And when you have infinite number of degrees of freedom, then in principle you can have infinite number of infinite amount of entanglement. And then turns out the consequence of this infinite amount of entanglement is actually to lead down a factorization of the a breakdown of factorization of Hilbert space. So now let me give you an example. So let's consider two infinite spin chains which are pairwise entangled. Okay, so here I have two infinite spin chains I call L and R. So each dot denotes a spin. Okay, so there's an infinite number of them, say, in the L system, and there are infinite number of them in the right system. But then these two spins in the left and the right, they're pairwise entangled. Okay. And so let's consider such a system. Okay, and then the physical Hilbert space are finite energy excitations, say, above such a configuration. So suppose we have such a configuration, and then let's imagine we consider the physics above such kind of configuration. Okay, and the physical Hilbert space would be just finite energy excitations on such configuration. Okay. And so physically, whenever you flip a spin, say here, imagine this, consider this this pair of spin. So now imagine we want to change the entanglement between them. We can flip the spin between them, and then that will cost energy. Okay, and so that means actually we the physical Hilbert space corresponding to the finite energy excitations means that in the physical Hilbert space we can only flip finite number of spins, and then this immediately implies that your physical space, the physical Hilbert space, cannot be factorized. Okay, in terms of the Hilbert space of the right system and the Hilbert space of the left system in the thermodynamic limit, which you have infinite number of the spins. So to see this is very simple, because if you want to have a tensor product structure, okay, means that you must be able to have a product state between the right system and the left system. And to have a product state means there's no entanglement between the right spins and the left spins. But in order to not have any entanglement between the left and the right spins, then you need to flip an infinite number of spins. Okay, because there are infinite number of them. Okay. And that costs infinite amount of energy. So that kind of operation is not in your physical Hilbert space. And then this means that your physical Hilbert space is actually not, cannot be factorized. Okay. So this is a heuristic argument, but you can prove this rigorously mathematically. Okay. So this gives you an explicit example. that when you have infinite amount of entanglement, actually the corresponding physical space actually cannot be factorized between the two parts, even though it's perfectly sensible. Physically, we can talk about the left system and the right system, okay, say as the subsystem. So another example is quantum field theory. So let's consider 1 + 1 dimension of quantum field theory on a lattice. So here I just only draw the spatial dimension. So here are the lattice points. And imagine it's separate. Yeah, so at each lattice point, there's some degree of freedom, say some number of harmonic oscillators. So now let's imagine separate the system into the right system and the left system. Okay, so the right system consists of the right, say the lattice point to the right of this separation, and the left corresponding to the left of this separation. And then say in the typical quantum field theory on the lattice, then there can be entanglement between the left and the right. So here I draw this dashed line, this red line, to indicate there's some kind of entanglement between them. Okay, so there are also entanglement between, say, further lattice sites, etc. So now let's consider the continuum limit. Take A go to the lattice spacing go to 0. Then in the continuum limit, then for any, okay, for any segment, okay, no matter how small, okay, in the continuum limit, there always infinite number of degrees freedom. Okay, that's by definition is the continuum limit. So no matter how small distance near the separation between L and R, there are always infinite number of degrees freedoms. Okay, and they're entangled with each other. And again, in this case, there's an infinite amount of entanglements between the left system and the right system. And in order to factorize, and the physical Hilbert space, okay, and then again corresponding to finite energy excitations in the continuum limit. Okay, that's how we normally define the Hilbert space of quantum field theory. And then that means, okay, any finite energy operations, okay, because there's an infinite amount of entanglement between the left and right, and any finite energy operations you cannot, okay, you cannot separate them into a product state. Okay, you can disentangle all the degrees freedom, all the infinite number of degrees freedom. Okay, and again, and then that means your physical Hilbert space cannot be factorized into those associated with the left and those associated with the right. Okay, and so this is another example, which even though there's infinite amount of entanglement, but as a result, the Hilbert space cannot be factorized. Any questions on this?
Yeah, isn't it possible like to make the energy depend in this case of the length, so that the condition that cannot be factorized is not really like a consequence?
Sorry, say it again.
Yeah. I mean, like if we make the energy when we have particles that are near one another, perhaps
Yes.
we need less energy to entangle them. Yeah. So when you go to the continuum, you basically almost need no energy at all. Yeah.
Oh.
Is that something like that possible?
Oh, good. That's a very good question. So you see, let's imagine, that's a very good question. Yeah, let's imagine first on the lattice. Okay, first on the lattice, you have the let's imagine this quantum field theory defined on the lattice. We are in the ground state of the system. Okay, we are in the ground state of the system, and in the ground state, and then this degree of freedom. For example, you can do a free quantum field theory, and because of the kinetic term, then those nearby degrees of freedom, they are all entangled. Okay, they're all entangled in the ground state. In the ground state. And now on the lattice, you can have excited states to which the left system and the right system are not entangled. Okay, and you just break all the entanglements in the ground state, and then it just use energy to break all the entanglement in the ground state. Then you can get some excited states which left and the right are unentangled. And indeed, on the lattice, you have factorization of the Hilbert space between left and the right. Okay. But now the claim is that for the system in the ground state, now you take the continuum limit. And now in the ground state, in the continuum limit, there's an infinite amount of entanglements between the left and the right. Okay, that just comes from taking the continuum limit of the ground state. Okay, which you can actually show this rigorously. Okay, and then there's infinite amount of entanglement between left and the right. And now those operations in the lattice, which can break the entanglement between the left and the right to get the product state, and those operations, their energy goes to infinity when you take a go to 0 limits. Okay, because they involve in breaking entanglement of infinite number degrees freedom. So those kind of operations, then they drop out in the continuum limit. Because in the continuum limit, we only want to keep the finite energy operations above the ground state. Okay, so that's how why the continuum limit and now the Hilbert space become no longer factorized. Okay, does this answer your question?
Yeah, pretty much. Thank you.
Okay,
I appreciate it.
Other questions? Okay, good. So now, when factorization of the Hilbert space does not exist, then how do we describe entanglement? Because you remember, we describe entanglement by writing down the wave function and saying that the wave function cannot be factorized into the states of the left and the right. Okay, they have to be superposition of the states of the left and right. So in order to define the entanglement in our textbook, somehow we rely on this factorization structure. Okay, but then how do we do? Okay, when factorization of the Hilbert space does not exist. Okay. And then how do we describe entanglement? So the standard practice in such a situation, for example, in statistical physics, in quantum field theory, the standard practice, what people do is people introduce a regularization. For example, people introduce a lattice spacing. Okay, people introduce a lattice spacing rather than considering a continuum. They introduce a lattice, and then they try to calculate the entanglement on the lattice, and then they consider, then they take continuum limit. Then of course the answer is infinite, but often in this infinite answer, they can extract some finite universal physics. Okay, so that's the standard practice. Okay, similarly with this spin chain example. Okay, you can just put a cutoff, consider the finite number of spins, and then you take the number of spins, go to infinity, etc. Okay, so the standard practice is just to regularize your system so that you have a factorization, and then you try to extract some universal information about the entanglement. But of course, this procedure is rather awkward, and it would be ideal, okay, to be able to describe the entanglement in such systems in an intrinsic way. Okay, yeah, because you can easily imagine, and by introducing this kind of regularization, and you can you actually meet some important physics which are intrinsic to this original system. Okay, so indeed we will see this is the case. Okay, and we will describe how actually describe entanglement in these more general situations. And so, so this takes us to the von Neumann algebras. So now let me first give you a very quick history of von Neumann algebras. So von Neumann was was a genius. In 1927, say 2 years after the discovery of quantum mechanics, okay, and he was like, I think 1927, he was something like a 24-year-old or something, and he's embarked on formulating the mathematical foundations of quantum mechanics. Okay, and all our modern concepts, say of quantum mechanics, say the operators, Hilbert space, and all these density operators, all these things, they all came from von Neumann. Okay. And at the same time, when he was formulating the mathematical foundation of quantum mechanics, it came naturally to him that it's actually very natural to define subalgebras of observables in the quantum system. Okay, and this is later called von Neumann algebras. Okay, and he just consider, say, let's consider some subsets of observables, which, for example, certain observers can access. And then let's just study, say, this subset of observables and to see whether one can say things about them, etc. Yeah, so this is the kind of things mathematicians like to do. Okay, and then in subsequent years, in particular, starting in the mid-30s, teamed with Murray. So Murray at that time was a fresh PhD, math PhD from Columbia. And then the von Neumann teamed up with him. Then they developed over quite a large number of papers, 4 or 5 papers. They developed the basic theory and the classifications of these von Neumann algebras, which the von Neumann first defined. And so von Neumann, and in particular, they can be classified broadly into type 1, type 2, and type 3. And so von Neumann himself had high hopes that von Neumann algebras should have important implications for physics and will play central role, so in physics. Okay, but he didn't see that day himself. He died very young at the 1950s. And since 1970s, say this von Neumann algebra has become a vast mathematical subject. But also starting 1960s, there's a very small group of mathematical physicists. They realize it's very natural to use the language von Neumann algebra for quantum field series. And so they developed so-called algebraic quantum field theory. And so even though people started using von Neumann algebra to talk about quantum field theory, and this is a very small field, okay? It's only a very small number of people, very dedicated, very good people, and working on it. So it's far from the mainstream, okay? And so for over, say, 50 years, there's a small dedicated group of people have developed this algebraic quantum field theory, and they have found many interesting results, etc. But has been not much noticed by the mainstream people working on quantum field theory. And then only during the last decade, okay, when we start thinking about, say, when people started thinking about entanglement in quantum field theory, in quantum many-body systems, in quantum gravity, did people actually recognize the connection of the von Neumann algebra to entanglement? Okay, so now I would advocate that the von Neumann algebra actually is the language for entanglement. Okay, is the best language for entanglement. Just like group theory is the language for symmetries, and the von Neumann algebra is the language for entanglement. And so now let me say a few words. What is in von Neumann algebra? So a volume algebra is very natural to define. So let's imagine we have a quantum system, say with some Hilbert space and then you can look at the operators acting on this Hilbert space. Okay, and now let's look at, say, some collections of operators. For example, if you are some observers, then you have access to some collection of operators, and then this operate, and then you would like to define the algebra of operators. And in order to do that, we normally define some completion of the algebra. Say they should be closed under certain procedures. And then it's very natural for this collection of operators to be say closed under Hermitian conjugation. Means that if an operator is in the algebra, is in the collection, and then its Hermitian conjugate is also in the collection. And then say they're closed under the operator product. Say if A1, A2 are in the collection, then A1 times A2 is also in the algebra. Of course. Yeah, by collection of operators, I always mean a vector space of operators. Okay, the superpositions of operators, of course, should also be part of the collection. And so we can also include the operator product, and then that defines the algebra for you. And the most important, which von Neumann defined as a requirement of this closure completion, is that this collection of operators should be closed in the limits in matrix elements. So this means the following. So let's consider some collections of operators, okay, some sequence of operators in this algebra A. And now let's imagine this sequence of operators have a limit. Okay, they are matrix elements among any states in your Hilbert space. Say has a limit, okay, to some other operator in your system. Okay, some other operator, they converge. Say their matrix element for between any states converge to some other operator. Then in this kind of situations, then we define then A then as a weak limit, so-called weak limit of AN. Okay. And then this von Neumann algebra then is the statement that this algebra should be closed under this limit. Means that if A is the limit of AN and all the AN is in the algebra, then A should be in the algebra. So this is a very natural requirement. It's because if A is the limit of those operators, and then we essentially can use A to A essentially just very close to the sequence of these operators when N is very large. Okay, then we should not. So normally physical measurement cannot distinguish them. Then it's natural that A is a part of your algebra. And also using the matrix element to define the limit is very natural because that's physically what we observe. And then now, so such the closure under such kind of operations then defines your von Neumann algebra. Okay. So this is a very simple definition, but it's actually a very powerful. Then of course people have developed this elaborate series of von Neumann algebras, etc. It turns out they have very rich physics and mathematical structure. But also, if you look at this definition, this is also very physically, it's also very natural. We can view this as a definition of a subsystem. So what we normally intuitively by a subsystem physically, by a subsystem, we just think about the subset of degrees of freedom, which we can access. Okay, we can manipulate, we can make measurements, we can say perform operations, etc. And this von Neumann algebra is precisely a collection of such kind of a very natural definition of such kind of operations. And then we can just simply define a subsystem as a volume algebra. Okay, we can just enlarge our definition of a subsystem by just defining them as volume algebras, rather than using the factorization of a Hilbert space. Okay, so we are already more than 1 hour. Maybe we can have a 5 minutes break. And okay, good. So yeah, so when you look at the definition of volume algebra, it seems like very naturally we can define it as a sub. We can use it to define a subsystem using it. Okay, so in other words, we can say a subsystem is a volume algebra, and conversely, a volume algebra can be viewed as a subsystem. Okay, and
can I ask you a question?
Yes.
Can the number of let's say the operators in a subregion can be infinite, or they should be finite?
So they can be finite. So they can have a say this volume algebra, say I will mention I think I will answer this question maybe in a few minutes.
Okay.
Just wait for the next slide, and if does not answer your question, just please ask again.
Okay.
So volume algebras, say Muir and von Neumann, they classified the volume algebra based on the properties, say, of its projection operator. We will not be able to go in detail, say, of the classification. Just to say that they can be classified into type 1, type 2, and type 3. And in particular, if A is a type 1 volume algebra, then you can prove that then there must exist a factorization of a Hilbert space, okay, into H1 and H2, and A corresponding to all the operators in the acting on the Hilbert space of H1. Okay. So in other words, whenever you have a type 1 volume algebra, there exists that guarantees a factorization of the Hilbert space. Okay, guarantees a factorization of the Hilbert space. And in this case, then you just reduce to the standard story, a standard textbook definition of the subsystem based on factorization of Hilbert space. So in the standard case, when you have a factorization of the Hilbert space, then we say H1 defines a subsystem. And then that's equivalent saying that all the operators in H1, when you define the H1 as your subsystem, then of course all the operators in the Hilbert space of H1 and corresponding to all your physical operations, and that's equivalent to the to our definition of A as the definition of the subsystem. So that means that this definition of the von Neumann algebra as this definition of subsystem as von Neumann algebras then actually recovers, okay, the standard textbook definition as a special case. And so and then this definition represents a genuine good say generalization of the standard definition. Okay. And then there are type 2 and type 3 situations. And then those type 2 and type 3 situations then apply to cases where factorization of the Hilbert space does not exist. Okay, then they will apply to more general situation. Now, of course, whenever you have a factorization of a Hilbert space, then it's always get type 1. Okay, so this is if and only if. Okay, so when you have type 1, you always have factorization of Hilbert space and vice versa. So this von Neumann algebras, say they crudely classified into say different types, and within each type they can be further classified. Okay, for example, in the type 1 you can classify into type 1n. So type 1n essentially just corresponding to you have an n-dimensional Hilbert space, say this H1, for example, you say if A is type 1n, and that means in this case, the H1 is an n-dimensional Hilbert space of finite dimension. Okay, and then A in this case would be just is all the operators is the on this n-dimensional finite n-dimensional vector space. Then of course A is just the matrix algebra of n by n. And then in this case, the A is just a finite dimensional vector space. Okay, so so this is an example which this algebra can actually be a finite dimensional vector space. But in general, if you view this A as a vector space, it's infinite dimensional. Okay, but in some special cases, like this type 1n case, it's a finite dimensional vector space. And you can also have the, suppose you can also have the case which H1 is infinite dimensional. And then of course, A will also be infinite dimensional as a vector space. And then in this case, it's called I infinity. And similarly, and then one can also further classify type 2 and type 3. For example, in type 2, corresponding to type 2.1, type 2 infinity, type 3 also separates into type 3, 0, type 3 lambda, type 3, 1. And lambda is a number between 0 and 1. Okay, so we are not going to those classifications. And you only need to know that they are classified by some further properties, say, of the algebra itself. Okay, some universal properties of the algebra itself. Okay, good. By the way, does this answer your earlier question regarding the size of the algebra?
Yes.
Okay, good. So now let's go back to our questions, to examples we discussed earlier. Let's go back to this entangled spin chain. So remember there we have this infinite chain, two infinite chains which are pairwise entangled. And so now let's imagine this, each pair is entangled as follows. Okay, so you have two spin. So the entanglement can be written generically as such an entangled state characterized by some angle theta. Okay, so this is a normalized entangled state between two spins. And say, for example, when theta is equal to 0, and then the two are unentangled. And when theta equal to, and we can also, and when theta equal to pi over 4, and then these two spins are maximally entangled. Okay, and then between 0 and the pi over 4, and then you have some partial entanglement between the two spins. And in this case, we can also naturally define the algebra, the subsystem associated with the left system and the right system, say, as the algebras of operations on the left system and the algebra of the operations on the right system. Yeah, just you can flip spins on the left, then corresponding to AL. You can flip spins on the right, you can then corresponding to AR. Okay, so the collection of those operations then is AR and A left. Okay. Again, keep in mind the physical operations are defined to have operations of finite energy. Okay, so they can also can only flip, say, some finite number of spins. So it turns out, so this can be established. Yes, I mentioned earlier that in this case, the physical Hilbert space corresponding to finite energy excitations cannot be factorized. But now we can define the subsystem using the algebras. And it turns out the algebra here, when the theta is equal to pi over 4, means that each pair of spin are maximally entangled. Turns out you can show that they corresponding to a specific type of type 2 algebras called type 2.1. Okay, so I will not go into details why this is type 2.1, etc. And it's only enough for you to know that this is not type 1. Okay, and this is some kind of type 2 algebra, which characterize this maximally entangled structure between the pairwise spins. And now if you consider some general theta between 0 and pi over 4, okay, non-zero theta between pi over 4, and then these two spins are entangled but not maximally entangled. then it turns out in this situation, for each theta, they corresponding to a different type 3 algebra. So this AL and AL are corresponding to the type 3 lambda. And each lambda corresponding to a different, and this lambda is different. And for just given by tangent square theta. Okay, so that means that for each different theta, you get a different type 3 algebras. Okay. And now we see the power of these von Neumann algebras. So if you using the traditional way of thinking about the entanglement, in the infinite spin chain case, the only thing we can say is that the two spin chains are infinitely entangled. Okay. But now, of course, the different theta corresponding to different entanglement structure. Okay, and when theta pi over 2, they are maximally entangled, and for different theta, the entanglement are different. They have different entanglement structure. And we see those kind of different entanglement structure are actually captured by the types of the entanglement, types of the von Neumann algebras. So for this maximal entanglement, and you see type 2,1, and then for each different theta, you can assign a different type of type 3 algebras. Okay, so we can say that the classification of von Neumann algebras actually provides a classification of entanglement patterns of quantum systems. Okay, and such kind of classification would not be available using the standard language. Okay, or factorization of Hilbert space, etc. Or entanglement entropies. So now let's go back also to this example of the quantum field theory, the sub-region quantum field theory. So we mentioned earlier, say if you consider 1 + 1 dimensional quantum field theory, when you separate them into left and the right region, and again the Hilbert space cannot be factorized with respect to the left and the right in the continuum limit. In the continuum limit, again, because of infinite amount of entanglements. But again, we can associate the operator algebras for the operations in the left and the operator algebras in the right. So the operator algebras are well defined. Okay, in the left and in the right, and so they define AL and A right. Okay, and now we can use them to define subsystems. Okay, AL and A right define subsystems. And turns out in this case, the infinite amount of entanglements between L and R give you a different, a larger type of von Neumann algebras called type 3-1. Okay, so that just indicates that the entanglement structure here is actually different from the entanglement structure of the spin chain case. Okay, different from the spin chain case. In fact, this type 3-1 is actually a universal result. You can show, okay, you can show rigorously, mathematically, that the algebra for general open region in the relativistic quantum field theory is always type 3-1. Okay, so these are just special examples which we consider half space. But just consider any general open region in the relativistic quantum field theory, and the algebra associated with that region, which you can define a subsystem, and that algebra is always type 3-1. And you can further argue that this type 3-1 structure actually has to do with the continuum of space-time and the causal structure associated with the relativistic theory. Okay, yeah, because you have a relativistic theory, there's a causal structure. It turns out that those structures requires the quantum field theory have a very specific entanglement structure, and which is offered by this type 3-1. Okay, so in this case, this type 3-1 structure reflects, okay, the entanglement structure required by the continuum and the causal structure. Okay, so keep this in mind. Okay, so even though I didn't define for you what is a type 3-1 algebra, you only need to know there exists such an algebra called type 3-1, and this type 3-1 actually can be used to reflect the continuum of space-time, causal structure, yeah, reflects the entanglement structure corresponding to the continuum spacetime and the causal structure. And again, this is an example that the classification of the volume algebra provides a classification of entanglement patterns, okay, in quantum systems. Okay, good. So I should also emphasize that the types of a von Neumann algebra only offers a crude characterization of the entanglement structure of a subsystem. Okay, so just like, say, you can classify the Lie algebras or Lie groups, and that kind of provides some kind of characterization. But the final entanglement structure, okay, can be extracted from the properties of a von Neumann algebra through many more powerful, say, algebraic tools, say, such as modular flows and other many. The theory of von Neumann algebra is a very large mathematical subject, okay, and with many mathematical results, which potentially can be useful for understanding physical systems. Okay, so the exploration of using von Neumann algebra to understand entanglement structure and is only really at very infant stage. Okay, and just like you can use Lie algebra, many detailed structure of Lie algebra to understand the symmetries of a system. Okay, good. Yes.
Yeah. The fact that you can describe relativistic quantum field theory with type 3.1, is that accounting for like any kind of interacting theories? Yeah.
Yes. Yes.
Okay. Okay.
So
Nice.
so here the statement is very general. It doesn't depend on whether your theory is interacting or free. What is important here is the continuum and the causal structure required by the relativistic structure.
Yeah. Do you have any particular reference that you will recommend us to read about this?
Oh yeah. So this is a fundamental result. So the statement that the von Neumann algebra associated with any open region in the relativistic quantum field theory is type 3.1 is a fundamental result in the algebraic quantum field theory, which was rigorously proven. And the saying that they reflect the continuum of space-time and the causal structure is more like a physical interpretation of those very mathematical results. Yeah.
Thank you.
And I can certainly provide the reference for the original mathematical results, and also there was a review by Wheaton also mentioned these results. And I'm also writing a review myself, which should be finished soon, which this is also discussed. Yeah. Mm-hmm.
Nice. Thank you.
Mm-hmm. Other questions?
Yes.
Yeah.
Sorry. So what would be the main idea to distinguish type 2 from type 3? So type 1 is that the Hilbert space factorizes, but what's the basic difference between type 2 and type 3?
Good. Okay. So the basic difference between type 2 and type 3 is the following. So in the type 2 case, you can define a trace for your algebra. You can define a operation called a trace. So remember, when you have a Hilbert space. Yeah, let me just very quickly go back. 1 second. Oh, sorry. I think 1 second. I think. Let me just hit. Right. Yeah. So let me just very quickly mention this. Yeah, so in this case, when you have a type 1, so when you have a type 1, if A is the algebra of some Hilbert space, then Hilbert space itself naturally offer a trace for the operators in this algebra. Okay, so in the type 1 case, you have a very natural trace, and in particular, this trace count the states. Okay, and if you have a projector, then this trace will count the projector will have integer dimension. So the type 2 corresponding to the situation, which even though you don't have factorization of the Hilbert space, but you can still define a trace. And that trace has very funny properties. Is that if you use the trace to define the dimension of a projection operator, and that dimension of a projection operator can be an arbitrary real number. Okay, so that trace have the funny property that can generalize the dimension of a vector space into a continuous real number. And so that's the special thing about type 2. And the type 3, such a trace does not exist.
Okay, thank you.
Yeah. So yeah, so von Neumann himself actually had very high hope for type 2. It's because of this trace structure in type 2 makes a type 2 algebra to be a very yeah, it's more like the following. Just imagine you when you have a type 1 situation, you have a Hilbert space, and you can talk about dimension of the Hilbert space. The dimension of Hilbert space is always integer or is infinite. But in the type 2 case, then you can actually talk about dimension in real numbers. Okay, you can talk about dimension in real numbers. It's more like to generalize the concept of the dimension to real numbers. Yeah, so that's the type 2. But in type 3, such kind of thing does not exist. There's no trace. Okay, you cannot talk about dimension. Yeah. Good. So does this answer your question?
Yes, thank you.
Okay, good. Other questions?
In the spin chain case, so should the theta equal to pi by 4 be viewed as a transition point from type 3.1 to type 2.1?
No, actually, yeah, actually it's not. No, actually, it turns out, yeah, this is a very good question. I think you are asking a very good question. Yeah, maybe, yeah, because I think maybe you are looking at the formula here. So naively, if you look at, I give you this formula lambda equal to tangent square theta. So when theta equal to pi over 4, naively you go to type 3.1. So, but
yeah,
it actually turns out it's not the case. So for any theta not equal to pi over 4, this formula applies. But then for theta equal to pi over 4, suddenly this becomes type 2.1. And somehow when you have a maximally entangled case, and there's actually special properties associated with those algebras, which is not present, okay, for the generic theta. And that's special properties then give rise to a trace structure, and then that makes it into type 2. Yeah.
Okay, thanks.
Okay, good. Okay, very good. So this now we can finally talk about in the last 20 minutes talk about the emergence of space-time using von Neumann algebras. And again, let's go back to this picture of anti-de Sitter space gravity and are related to the boundary theory. And we want to understand how the box space-time emerge from the boundary degrees freedom in the n go to infinity limit. Okay. Again, I emphasize that the finite n in the box, you just have fluctuating space-time. Space-time just fluctuates, which you don't have a geometric concept. And then the geometric concept, all those things should emerge when we take n go to infinity limit, okay, in the semi-classical limit, which is the G Newton goes to 0 limit. And so before I talk about emergent space-time, we have to first also accept ourselves what we mean by emergence of space-time. Okay, when we say emergence of space-time, we not only say the space-time itself, say including all the geometric concepts, say like the metric, say the causal structure, different subregions, and etc. But also all the physics on that space-time. Okay, so in the semi-classical limit, all the physics in the space-time, of course, just described by quantum field theory in the closed space-time. Okay, and so what do we mean by emergence of space-time is that in that limit, we should not only GR should emerge, we should also emerge is the quantum field theory in the curved space-time. And the conventional thinking for the emergence of space-time, people just normally have in mind that the emergence of the metric, and then the Lagrangian emergence of the metric, and say make the Einstein action, then plus the Lagrangian of quantum matter on the space-time. Okay, and indeed, this is one way one can think about the emergence of space-time and all the physics in that space-time. And this is the intuitive from normally our Lagrangian formulation or path integral formulation, say of the physics. Okay. But in this formulation, when you write down just say the Lagrangian or a general metric, and there are many important physics are not manifest. For example, the local physics, say definition, by local physics, we say you define an open region in your space-time, and you ask all the physical operations within that region. Okay, as we mentioned, that will define a subsystem for you. And the local physics and the causal structure, entanglement structure, all these things are not manifest. Say if you just give me a action and just give me a path integral of that action. Okay, it's because of all these kind of physics, the local physics, causal structure, entanglement structure, this concept have to do with subsystems. Okay, so in order to understand emergent space-time is those physics manifest, and then we need to have alternative approach, which is the emergence of the subsystem, which is manifest. Okay, so indeed, there's an alternative way to think about emergence of space-time, which is equivalent to this metric plus the Lagrangian approach, which is by considering the collections of all physical operations in all open regions of your space-time and their relations. Okay, so this is also a way, this is also the starting point of the so-called algebraic QFT. Instead of starting with the Lagrangian, we ask, just give you any open regions in your space-time, how you characterize the physical operations in those open regions and their relations. Okay. And for example, so let's consider, say, in the semi-classical limit of the ADS space-time, we consider, say, 3 subregions, O1, O2, O3. And say when we characterize their relations, we say the O1 is a subset of O2. So physically, that means that all physical operations in O1 is included in all physical operations in O2. Okay. And then O1 and O3 are space-like separated. Okay, so that means that the physical operation in them commutes. Okay, and of course that reflects the causal structure. And so this algebraic QFT, so this algebraic way of thinking about emergence of space-time, and then concerns the physical operations of all these different regions and their relations. Okay. And then we understand the emergence of space-time, then if we understand emergence of all physical operations and in all open regions and their relations. Okay. And it turns out this way of understanding emergence of space-time is very natural in the context of this holographic duality or this ADS CFT relation. Okay. And so this is so with my former student Lloyd Hauser, we proposed a way this is realized called subregion subalgebra duality. And this is the following statement. We say in the angle to infinity limit, each Bach subregion in the Bach, okay, in the gravity side, is actually dual to an emergent type 3-1 monomer algebras on the one type 3-1 monomer algebra on the boundary. And so as example, let's again consider the angle to infinity limit, which is a semi-classical limit on the gravity side. Say, suppose we consider these three regions, O1, O2, and O3, and then associate with each region, say, for example, O1, we associate some type 3-1 monomer algebra on the boundary side. And similarly for O2 and O3. And then the physical, then this algebra then captures all the physical operations in which region. Say, for example, A1 just captures all the Bach physical operations in O1. And this way, we can understand the emergence of space-time and the relation between all these subregions. Say A1 is emergent in the following sense, that this algebra either arises only in the angle to infinity limit, or it arises due to an infinite amount of entanglement in this limit. Okay. And again, this type 3-1 is needed to capture the Bach local physics and the causal structure. Okay, remember we said earlier, type 3-1 structure can be used to characterize a continuum structure and the causal structure. And indeed, the type 3-1 here is now used to capture the Bach local physics and the causal structure. Okay, and and then with the subregion subalgebra duality, then for example, we can for example, the relations, the fact that O1 is a subset of O2, then can be captured on the boundary side that the corresponding algebra A1 is a subset of A2. And O2 and O1, although O3 are space-like separated, and then just captures that A1, their corresponding algebra on the boundary, they commute with each other. Okay, so this way we can have an algebraic formulation of the causal structure in the Bach. Okay. And then the Bach entanglement structure of O1 then reflect to the type 3-1 structure of A1. Okay. So do you have any questions?
Yeah, I would like to know how is that those bulk regions and like each one having like a meaningful boundary in which we can like study like their respective algebra, if I'm understanding correctly, right?
Yes, yes. Sorry, what's your question? So which region has a dual algebra?
My question is like I have the bulk structure one, like how I end up like identifying which one is their boundary, right?
Yeah, means that say, suppose you have some operation in O1, and then that operation we can find a corresponding element in A1 which does that operation in O1. Yeah.
Okay.
Yeah, was this what you were asking? Yeah, just means that any operation you can perform in O1, we have some corresponding element in A1 which can realize that. Yeah, so that we mean by this region is described by this algebra. And then all these relations between those regions then can be captured by the algebraic relations on the boundary theory. Okay, so now let me give you an example of the power of such kind of thinking. So let's consider the thermofield double state. So now let me just, for simplicity, represent the boundary theory by a plane. By this plane, just it's easy to to draw. Okay, suppose now let's consider two copies of your boundary system. Okay, and so boundary you have let's call them R and L, so two copies of boundary system. And now let's suppose we put them in the entangled state. Okay, so this -9 means we put these two systems in the entangled state. So your full Hilbert space is a Hilbert space of the right CFT, the right boundary system, which I call HR, and the Hilbert space for the left boundary system, which I call HL. And the full system, of course, have a tensor product structure. Because of each of them, of course, each boundary system have their own Hilbert space. And now I consider this entangled state, and they're entangled in such a way, which is called the thermal field double state. And in the thermal field double state, the L and R system are entangled in a very specific way, such that if you look at each subsystem alone, it appears as thermal. Okay, and say if you trace out the other system, if I only look at the observables in the right system by tracing out the left system, then the right system appears to be thermal, and vice versa. Okay. So the thermal field double state is a powerful way to describe, say, the thermal ensemble using the standard quantum mechanical language. Okay. Yeah, using a pure state. Okay. And so now we can look at the, say, now let's look at the operator algebra of the left system. Okay, so let's focus on the operator algebra of the left system. Similarly, you can do it for the right system. So now let's first consider the finite n. So these are just some ordinary quantum mechanical system with some operator algebras. Okay, and you have some Hilbert space, and the BL is just all operators on this acting on this Hilbert space. But we are interested in the limit of the Lagrangian limit. We want to see how the space-time geometry emerges in the Lagrangian limit. And so at the finite n, so these are the type 1 von Neumann algebras because they just operate algebra on some Hilbert space. So we are interested in n go to infinity limit. And so we call the n go to limit of this algebra XL. Okay. So when you take n go to infinity limit, it's similar to the continuum limit we talked about earlier. So when you take the continuum limit, certain operators in your finite NC in your lattice, in the continuum limit, certain operator in your lattice theory, say of your QFT, they corresponding to infinite energy operations, and then they just drop out in the continuum limit. So similarly here, when we take n go to infinity limit, the certain operations, certain operators, they may correspond to infinite energies, and then they will drop out your infinite, n go to infinity limit. So so we need to then examine the limit carefully, and then only look at those operators which have well-defined limit. So we denote those operators which have well-defined limit XL. Okay, and so corresponding to those operators in BL which have a good limit. And so turns out what happens to the system in the n go to infinity limit actually depends on the temperature. When the temperature at low temperature, when the temperature is sufficiently low, the entanglement between the L and the R system actually turns out to remain finite as n goes infinity. So yeah, you remember this is a thermal field double state, and you specify the entanglement by requiring each system appear at some kind of temperature. Okay, so essentially the value of temperature determines the bound of entanglement between the two systems. And so at low temperatures, there's not much entanglement. Then the entanglement between the L and the R actually remains finite when you take n go to infinity. So in this case, because your entanglement between finite, then this is just our ordinary situation, which you have finite amount of entanglement, and you just have the type 1. Okay, so that means here in the infinite n limit, your Hilbert space can still be factorized. So recall that each boundary system is dual to ADS. Okay, so now you have two copies of the boundary system and entangled by some order 1 entanglement. And then naturally, this just due to the two copies of ADS, which these two copies of ADS, they're just entangled by some order 1 entanglement. Okay, so at sufficiently low temperatures, when there are order 1 entanglement between the boundary series and then in the angle to infinity limit, then the gravity side just described by the two copies of your ADS space-time, and then these two copies are entangled, the degrees freedom in these two copies are entangled. Okay, but now let's look at sufficiently high temperature. It turns out that at sufficiently high temperature, the entanglement between the L and R system actually become infinite. Okay, so if you calculate the entanglement entropy between L and R, they actually diverges when you take angle to infinity. So in this limit, again, we can examine what happens to the operator algebra in this limit. Okay, and when the entanglement become infinite. So now you can show actually in this case, the algebra become type 3-1. Okay, this algebra become type 3-1. So this is what I mean, the emergent type 3-1 algebra in the previous slides. Okay, so in this case, the algebra associated with the right system actually now, instead of being a type 1 algebra, now become a type 3-1 algebra in the angle to infinity limit. Then that means actually the Hilbert space for the full system cannot be factorized anymore. Okay, so that means now in this large N limit, despite the appearances, you can no longer have a the Hilbert space for the full system can no longer be factorized into that for the left system and the right system, okay, as angle to infinity. And then what happens on the gravity side? It turns out on the gravity side, rather than have two disconnected ADS, now there's a wormhole to connect these two boundaries. And now they connected through a wormhole in the Bach. Okay, so the Bach now, so this non-factorization of the Hilbert space is reflected on the gravity side through an emergent wormhole. Okay, and this two universes corresponding to the two ADS are now linked by a wormhole in the Bach. Okay. So you can just draw a Penrose diagram of this relation. So this is the standard relation that at sufficiently high temperature, two copies of the of your boundary system in the thermal field double state is actually due to an internal black hole in ADS. Okay, and the two copies of the boundary system then corresponding to the two boundaries in the black hole geometry, then they're connected through this wormhole in the Bach. Okay. And for many years, there has been a puzzle between this picture, because the right-hand side, the two systems are factorized. But on the left-hand side, they're connected through this wormhole in the Bach, so they cannot be factorized. So this is what is called the factorization puzzle. Okay, but by considering the nature of the boundary algebras, in particular their emergent nature in the large N limit, we explain this factorization puzzle. Okay, we explain this factorization puzzle. And there's a lot of more puzzles associated with this identification. So one puzzle is a lot of puzzle is where does the horizon correspond from this boundary picture. Okay, so the boundary has a time t which can be continued into the Bach corresponding to the Schwarzschild time, but Schwarzschild time ends at the horizon. Okay, t equal to minus infinity. And then how do we describe in the boundary theory this emergence of the horizon? Okay. And furthermore, how do we describe actually this future region in the Bach? Because the time, because the extrapolation of the boundary time stops at the horizon. And furthermore, we can actually send stuff okay, into the future region, and they can in principle interact in the future region. Okay, but the boundary system, they're just corresponding to entangled system. There's no interaction between them. Okay, so this is also called the causality puzzle. Okay, and in the not only they're connected by the wormhole in the block, they're actually causally connected through this future region. Okay. Okay. And so I will not have time to explain how we resolve those puzzles. Let me just very quickly mention, quickly mention that this F region and the to describe this future region, you actually need to describe the Kruskal time, which can extend from the Schwarzschild time to the Kruskal time, which can describe the future region. So it turns out that this Kruskal time can be shown to emerge in the boundary CFT precisely from this emergent type 3-1 structure, and through something called the half-sided modular flow. So, I will not be able to, I will not have time to describe the construction, but turns out that this type 3-1 structure gives you some additional structure called half-sided modular flow, which can be used to explain the emergence of the Kruskal-like time on the gravity side. And then that can be used to describe how, say, how you can take, say, operate in the R region, and then you can just transport it, evolve it into the future region, okay, through this Kruskal-like time evolution. And in particular, when you cross the horizon, then the evolution will exhibit certain non-analytic structure, and then give you the signature of the horizon on the boundary theory. Good. So just to summarize, we argued that in the angle infinite limit, the boundary system become infinite entanglement, and then that leads to new emergent type 3-1 structure, and then that also give rise to box space-time and all the physical operation in it. Okay, and I used this thermal field double example to illustrate this. So do you have any questions?
Yes, I have a question. You said that this wormhole picture only emerges at high temperature.
Yeah.
Is this transition between wormhole and no wormhole understood as a function of the temperature? How one goes from one picture to the other?
That's right. Yeah, that is understood. So yeah, that transition is pretty well understood. It's pretty well understood from various different perspectives. But from this algebraic perspective, it's still not fully understood. Just how you transition at the low temperature from this type 1 algebra into type 3-1 algebra at sufficiently high temperature. How does this transition happens? I think it's not fully understood, but the transition itself can be understood from many other perspectives. And so, for example, by Euclidean path integral, etc. And so from those perspectives are pretty well understood. Yeah.
Okay, thank you.
Yeah. The fact that there's a transition is well understood. The fact that there's a transition from low temperature to high temperature, that your entanglement become infinite, and that's well understood. For example, you can do Euclidean path integral, etc. But really, how the algebra transits and how the black hole emerges, I would say that's still not fully understood. Yeah. Mm-hmm.
And when you say it's understood, it's like in general setups or very particular cases like JT gravity or very fine-tuned low-dimensional models.
Right. Yeah. Just say in the boundary theory, you can argue for the existence of a transition generically for general matrix quantum systems. And so you can have very general argument showing that generically in the Lagrangian limit, you will have such a transition. And of course, the detailed transition is hard to work out if you have interacting theory, but the existence of the transition can be argued pretty convincingly. Yeah.
Thank you.
Yeah, using some Euclidean calculations. Yeah. Mm-hmm.
I think there is something that I didn't understand about the factorization puzzle. So
Okay.
at above the high temperature, in the high temperature limit, the boundary algebras become type 3 one, right? So they
Yeah.
do not factorize.
Yeah. That's right.
So
They do not
what?
factorize. Yeah.
So what is the puzzle? If the if boundary algebra doesn't factorize and the algebra in the bulk also not factorize, then what is the puzzle?
Oh, yeah. So previously didn't have this picture, right? Just previously, we only have this picture that the block is connected. The block connected, there's no factorization, but the boundary is factorized. So the resolution of the puzzle is, yeah, this picture was already known from 2001, but understanding from this algebraic language is only during the last few years, right?
I see. So okay. So the puzzle is that the bulk is connected and the boundary is not connected. It doesn't have anything to relate with the factorization of the boundary algebra or the bulk algebra, right?
Sorry?
I mean, the factorization puzzle doesn't have anything to do with the factorization of the boundary algebras and the factorization of the bulk algebra, left and right algebra.
No, they do. Naively, in the boundary theory, if I give you this picture, then there's a factorization of the algebra in the boundary. But there's no such factorization of the algebra in the bulk. So that was the previous puzzle. But now we explain it by saying that indeed in the Lagian limit, even the boundary algebra cannot be factorized.
Oh, I see. Okay.
Yeah. You can define the AR and AL. You can define the algebra corresponding to the right system and the left system, but there's no factorization of the Hilbert space associated with them. Yeah, previously, if you just look at this naive picture, there's a factorization of Hilbert space associated with them, and that seems to contradict with the Bach picture. Yeah.
Okay, thank you.
Right. So I'm running out of time. So yeah, I have some brief philosophical remark I can either make or not make. So yeah, and we can also just finish now. Whatever you prefer. Yeah. Mm-hmm.
Yeah, please go ahead.
Okay.
It's okay.
Yeah. Let me just say a few philosophical remarks. So this sub-region, sub-algebra duality is actually reminiscent of something called the Gelfand duality in the mathematics. So the Gelfand duality in the mathematics is the following statement. Say if you want to define, say, a topological space, okay, rather than try to describe the topological space geometrically, say using the open set and the relation between the open set in that space, you can equivalently define that topological space by considering the algebra of functions on that space. Okay, that turns out to provide the equivalent formulation of the topological space by using algebras. So by looking at the algebra of functions, actually you can characterize all the geometrical information. And that's the Gelfand duality has been generalized, in particular has been used as the starting point of formulating the concept of the non-commutative geometry. So of course, for the ordinary space, the algebras on that space are commutative. But now if you consider non-commutative algebras, then provide a generalization of your usual notion of geometry. And so that provides the definition of non-commutative geometry. Okay, so again, this is a huge subject in mathematics. And so this philosophically, this sub-region, sub-algebra duality can be considered, say, as a vast generalization of the Gelfand duality. So by using the boundary algebra to, in the larger limit to describe the emergence of the space-time in the bulk, we're not only using those algebras to describe the emergence of geometry, but also all the physical operations in that kind of space-time, in that kind of geometry. Okay. And so this kind of algebraic language gives us a very general and flexible language, okay, to talk about space-time and the physics in it, okay. And so in particular, it may be valid even in the stringy or quantum gravitational regime. So remember I said that this kind of picture of geometry is only valid in the semi-classical limit, which we cannot resolve the strings, or we cannot we don't have significant quantum gravitational effect. And beyond, when you go to stringy regime and or go to quantum gravitational regime, our conventional concept of the geometry just does not apply. So it's possible that this algebraic language actually provides a way, okay, which naturally extend into those regimes. And we actually also had some papers trying to do that. Yeah. Mm-hmm. Good. So using this operator algebra to understand quantum gravity also brings new power tools for understanding many other questions. And for example, there are many other works. Let me just quickly mention. So there have been new understanding of de Sitter entropies, and also new understanding of generalized entropies, and also you can use it to generalize this wormhole picture I mentioned earlier, and to into something called algebraic ER equal to EPR to describe emergence of space-time connectivities, and also formulations of stringy black holes, etc. Okay, and also you can actually do it using the to describe some enhancement of quantum tasks, etc. Anyway, so there are many questions. And already they have a lot of results. Yeah. So finally, let me just very quickly mention. So Hilbert space plays a fundamental role in quantum mechanics, but in quantum gravity, there are indications that Hilbert space is actually not fundamental. Okay, in quantum gravity, I won't have time to describe here, but there have been many indications. But actually it's a direct concept. So maybe the algebraic way, maybe the algebra way is a more fundamental way to think about quantum gravity. So hopefully we are not too far from it. Okay, yeah, thank you.